Good evening. This recording is for Algebra 1, Chapter 9, Lesson 2, Graphing y equals ax squared plus bx plus c. If you remember from the last video, b affects the position of the axis of, well, you probably don't remember that, but I didn't talk about it. The value of b affects the position of the axis of symmetry. If there's no bx, which we did talk about in the last video, if there's no bx, the axis of symmetry is the y-axis. But if you have an A, it's going to dictate the direction of the parabola of either an up or a down parabola. And then if you have a C, it's going to tell you where the vertex, or excuse me, not the vertex, where just the line hits the y-axis. So basically it's the y-intercept. Alright, so again, if there's no, when the axis of symmetry, no. There you go. Oh, wait, no, that's the same. Okay, so again, when the line or the parabola hits the y-axis, and again, if there's no bx, that means that the vertex is on the axis of symmetry, which is the y-axis, but if there's a bx, the axis of symmetry may not be the y-axis. Alright, so this, figuring out the axis of symmetry, there's a formula for it, and you can kind of figure out how they got to it by just graphing a bunch of parabolas. They basically end up figuring out that when you have a b, if you take the opposite of it and divide it by 2, well, 2 times the a, you're going to end up with the axis of symmetry. And there's some very big math that can go into this to prove it. But other than that, you can just kind of look at this graph. It's inside your textbook. These graphs, and they will show you basically how they get to it every time. It's basically the opposite of b divided by 2 times a. Alright? And so it's just something you need to memorize for now. It falls out very neatly later on in math. You'll learn how to do it, but for right now, just understand that it's this formula. Okay? Alright, so again, pattern led to the formula of the axis of symmetry, which is when you have a bx present. And again, it's negative b over 2a. Alright? Okay, so to graph y equals ax squared plus bx plus c, it's basically anything with a bx. First, you must find the axis of symmetry using the equation. Then you need to determine the y-intercept using c, and then you need to plot some points using the x-coordinates from one side of the axis of symmetry. And normally what it is when you're picking points to use for x, you're going to use the points of the axis of symmetry to the y-intercept. Okay, those will give you some points. Sometimes it gets a little hairy, especially if if the axis of symmetry is very close to the y-axis. It gives you few points to pick from, but it usually gives you a good starting point. And then you don't have to like guesstimate funky x's to plug in there. Okay, and then we're going to use the reflection of each point from the axis of symmetry to the y-axis on the opposite side of the y-axis with dots to complete the parabola. Okay, so here is an example problem. We're going to go ahead and use f of x, and again a fancy way of saying y, is equal to x squared minus bx plus 9. So again, the first thing we're going to do is find the axis of symmetry. So that would be a is 1, because there's nothing in front of the x, so there's the invisible 1. B is a negative 6, and we're going to do the opposite of negative 6 divided by 2 times 1, which is going to give me positive 3. So the axis of symmetry is positive 3, and I'm going to use a dashed line because it really doesn't mean much right now. It's just to help us know that it's there. Okay? Then the second thing we're going to do is find the y-intercept, basically, or excuse me, yes, the y-intercept. And basically the y-intercept is whenever x is 0, what we have left over. Well, that would be 9. So if f of 0 is 0 squared minus 6 times 0 plus 9, well that means f of 0 is 9, which means the y-intercept is 9. Boom, there it is. Alright, so now we have some x's that are between, and what I mean between, basically here, between the axis of symmetry and the y-intercept. It's going to give us some points to use. Okay, so let's go ahead and use them. Let's go ahead and use 0, 1, 2, and 3. So since I'm using 0 as x, I already know what it is. That's the y-intercept. It's basically c. So let's go ahead and use 1 next. Now we already know that the axis of symmetry is either going to be my highest point or my lowest point on the of the parabola. because remember, the axis of symmetry is where the parabola turns around. It makes a U-turn because parabola is a U-shaped, remember? Okay, so let's plug in 1 in there because, again, 1 is between the y-axis, the y-intercept, and the axis of symmetry, and I'm going to get 1, 4, which is right there. I'm going to plug in 2, and I'm going to get 2, 1, which is right there, and I'm going to get use 3 as x, which is going to give me 3, 0, and it makes perfect sense. I actually got to my axis of symmetry. Yay! So again, 3, 0 is the lowest point of my parabola, and then I'm going to use the reflection of each line on the left to create the new points on the right, which is the reflection. There we go. There we go. And there we go. And then I'm going to connect the dots. There we go. All right. And again, I know this is an upward facing parabola because I have a positive x. I know that the y-axis is 9 because of C, and because of what I know about the axis of symmetry, I can figure out where the lowest or highest point of my parabola is. There you go. All right, moving on. All right, and so it's an upward parabola. Yay. Okay, so this is a real-world application problem. We can use the formula height is equal to negative 16t squared plus vt plus c to describe an object's approximate height above the ground given an initial upward velocity, which is v. So v is how fast it's traveling, where gravity is the only air acting force. So again, we're not taking air velocity or air resistance into account when we're doing this. It's kind of like what physics likes to do. They like to all right, in a perfect world where the only thing acting on this ball is gravity, go. So that's basically what we're doing. So gravity is basically this negative 16 thing. T is time. T is time from when you either throw a ball, a rocket takes off, basically from when you start observing the object and measuring its height to when you stop measuring the object and its height. Okay? And just like in the previous question, C is how high something starts at. It is the y-axis. It is the y-intercept. It is how tall something is from the ground of 0, how high its height, from when you start the timer. So when time is 0, how high your object starts at. Okay? So here's an example. Let's say we have some time and some height, and we're going to launch a rocket. And this rocket actually is going to start underground right there, because it's at a height of 0, and it's going to take off. It's going to be going at a certain velocity, and it's eventually going to have gravity take effect, and it's going to come back to Earth. All right, so as time passes, basically, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, whatever, blah, 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 we can tell how high it is based on this formula, which is pretty cool. And this is actually how some of the first rocket scientists actually determined how high their rocket went, was by timing it. And they could use this very simple formula, a very elegant formula, to then determine the maximum height based on, they would time it and know how fast it was going, and then based on how long it took it to come to Earth, they would actually be able to figure out how high it went. It's totally awesome. Okay, moving on. So there's my rocket's parabola, and the highest point is actually the time at which the axis of symmetry happens, and since you knew how to determine the axis of symmetry, you can figure out the highest point. It's totally awesome. Anyway, so there you go, and then again, the y-intercept tells you at what height the time started. Okay, so, yeah, the starting point. Okay, so let's move on to the next one. Let's say a ball is thrown into the air with an initial upward velocity of 45 feet per second. Its height, h, in feet after t seconds, given by the function h equals negative 16t squared plus 48t plus 4. Try and visualize the parabola, guys. Which direction is it facing? Well, since we have a negative 16 in the A position, we're going to have a downward parabola. Basically, the ball is going to go up, it's going to reach its highest point, and it's going to come down. We know how fast the ball is traveling. It's traveling at 48 feet per second. That's a fast ball. And the ball was released at 4 feet above the ground, because that's where our time starts. Alright, so what does the 4 represent in the equation? It's basically how high the ball was when it started traveling 48 feet per second and the time started. At time 0, that's how high the ball was from the ground. Okay? And in how many seconds will the ball reach its maximum height? Well, that, my friends, is the axis of symmetry. Because we know that the highest point, the vertex, will lie on the axis of symmetry, we can actually figure out how many seconds the ball will be at its maximum height. Okay? Because, again, the axis of symmetry is along the x-axis. It's telling us at how many seconds this will happen. All right? And we can figure out, again, the ball's maximum height using the axis of symmetry and then plugging in some numbers. Okay, so let's go ahead and do this. So again, A is the downward parabola, B is the velocity of the ball, C is the height of the ball when it's released, and it's at the time 0. All right, so again, visualizing, we have a downward parabola, axis of symmetry. I've said all this, but now you can see it. And it's also the highest point of the ball, maximum vertex. Beautiful. All right, and then the axis of symmetry is negative b times 2a, which means we're going to have a x of 1.5, which is the axis of symmetry. It's already on there. That's just because I really liked my drawing, so I wanted to reuse it. And there's the axis of symmetry. And the y-intercept is going to be 4. Now again, this is very rough because I don't have a very exact drawing, but we can already take a look. So there's the blue guy, and he's very tiny, but he's going to throw a ball, and the moment he releases the ball is when we start caring about time, and it's also how high the ball is from the ground. Okay? So let's go ahead and do some math with this. We have the time, we have the formula, and we want to figure out the height at each time increment. Well, here's where we're going to pull our time increments. We're going to check it at half a second, 1 second, and 1.5 seconds. We're going to do it at half a second just because it's half a second after the ball's thrown, 1 second just to give us one more time point, and we're going to do it at 1.5 seconds because it is the axis of symmetry. It is the point where the ball is going to be at its highest. We want to know how high this person actually threw it because they're throwing it kind of hard, 48 feet per second. This thing is like taking off, man. I would not want to get beamed with a ball that's going this fast. Okay, so let's go ahead and take a look at those times. We have a half second, 1 second, and 1.5 seconds. Let's go ahead and do some math. And at half a second, the ball is 24 feet above the ground. 24 feet above the ground. This thing is taking off. That's like a 2.5-story building or something like that. At 1 second, the ball is at a height of 36 feet. And you guys can see those orange dots that I'm giving you. Those orange dots. There's one, and the next orange dot is going to be at 1.5 seconds, which again, highest point of the ball. Let's do some quick math. And again, at 1.5 seconds, we're at a total of 40 feet. 40 feet. That is the highest the ball is going to get if you throw the ball at 48 feet per second up into the air. Okay? So, and again, you can do it straight up. It doesn't quite matter at this point, but the highest that ball will get is 40 feet, and it is after 1.5 seconds has happened since you threw that ball. So 1/1000, that ball's way up there, about a 40-story building. All right, now to see how long it's going to take the ball to return to Earth and at what time it's going to hit the ground, because it's also very important to know when it's going to hit the ground, we can use the reflection of the points we just made to figure out when it's going to hit the ground. So it's going to hit the ground right after 3 seconds. Okay, so if it took 1.5 seconds to go up, it's going to take about 1.5 seconds to come back down. All right, it's actually going to hit the ground a little after it was thrown, because this is actually not perfectly symmetrical, because again, the ball left 4 feet above the ground when it started this travel. Now it's going to end on the ground, which means it's going to have a 4-foot difference from when it started, from when it's going to finish its symmetrical move and hit the ground. Okay? All right, so we can also use the same formula with inequalities. Yes, shading, guys, it's never going to go away. If you can do it with an equation, you can do it with an inequality. So the big thing is, do what you've been doing for this previous part of this lesson. Just remember, is the line dashed or solid? And remember to do a test point and shade. So we find the axis of symmetry the exact same way. Negative b over 2a. There it is, axis of symmetry. Now the y-intercept, well, that's just -5. And do some quick math with the x and y coordinates. So I'm going to plug in some points. Since this is an upward facing parabola, I don't necessarily, you know, I can always take more points than are between the axis of symmetry and the y-axis. It just kind of helps if you need to spot check. But since there's such a small space between my axis of symmetry and my y-axis, I can take numbers more further, just so that I don't have to deal with, hey, I'm going to use like 0.25 of a point and 0.5 of a point and 0.75 of a point, because A, it's hard to graph, and B, I don't want to have to take care of so many decimals. So I will have one decimal in there, 0.5, just so that you guys can see it. But if you can pick other points that are integers, it'll just make your life easier to graph, and it'll make your life a little easier to calculate, especially if you're not using a calculator to do all of this. So here are the points I'm going to use. I'm going to use 1, negative 0.5, and negative 1. Again, I'm using negative 1 because it is the lowest point of my parabola, because it lands on the axis of symmetry. Alright, so let's do some quick math, plot some points. There you go, there's another point. There's the next point. And here's my final point, and then I'm going to use reflection to graph the other points. And remember, a solid line is less than or greater than or equal to, and the dashed line is the less than or greater than. And draw on my lines, there they are. Now to test a point. Whenever you have an inequality, you have to test a point. You have to shade. There is no way around that. Alright? So, I can use the point 0, 0 because it doesn't land on my line. And I'm going to plug in 0 for x and 0 for y, and does it work? Is 0 less than or equal to negative 5? No, it is not. So I can't shade where 0, 0 is. I have to shade outside of 0, 0, which is there on the edges. Isn't that beautiful? There it is, guys. Okay, I'm done talking at you. Bye.